First thing I'm going to notice here is the molecular formula. It's important to keep that in mind as you're starting to think about the structure, because obviously what you come up with has got to fit that. So notice how many carbons, how many hydrogens, but notice those other elements as well. Even though they won't sort of show up directly in NMR spectra, they obviously affect the chemical shifts, and so you need to be thinking about them as you're interpreting the shifts in what you see. Then I'll look at information from any other kinds of spectroscopy before I get stuck into the proton NMR. And I think it's important to do it that way around, because interpreting other kinds of spectra, infrared, carbon-13, NMR and so on, is generally much easier. So do it first, and it will only give you limited information, but it will give you important clues when you're interpreting the NMR. And in this case, that peak 1630 to 1820, you probably know already, but if you don't, your data sheet will tell you that tells you you have carbonyl groups. So there could be one or more carbonyl groups in the structure. And again, that's going to be important when we're interpreting the proton NMR. So that's all the extra information we have to go on for the moment. So the way I start approaching the proton spectrum, which is what we're going to do now, is just to pick one peak. So I'm going to pick this one at the end there, and we're just going to see what can we learn from that peak. So first thing to notice is the peak area. If you look at all of the peaks and add up their areas, you've got 3, 4, 5, 6, 7, 8, and you can see that equates to the 8 hydrogens in the structure. That means that the numbers, the individual peak areas, equate to the numbers of hydrogens causing that peak. You just need to be careful with that, because it might have been possible, if I'd added up all the peak areas, that they would only have come to 4 rather than 8, and that would have meant that each peak area unit corresponded to 2 hydrogens, and you get that when you have lots of symmetry in your molecule. But we haven't got that here. So we've got total area is 8. There are 8 hydrogens, so each area unit corresponds to 1 hydrogen. Okay, so we can write that down and say, right, that this has an area of 3, and we can explain what that means, that 3 hydrogens contribute. And when you get that situation, it's very likely that that means you've got a CH3. You can imagine it's possible you have 3 separate CHs which are all equivalent, but that's kind of unlikely, especially when you haven't got that many carbons to play with. So it's very likely that that's a CH3. And somewhere in the back of your mind, you have to be clear that it's not certain. Sorry, I can't seem to write on the screen here. So that's likely a CH3. So we can write that down. We can say, right, we think we have a CH3 in the structure, and obviously because carbon must form 4 bonds, that CH3 has got to be attached to one other thing. So we can draw our 1 bond in like that. What else does this peak tell us? Well, what about its chemical shift? Well, that's consistent with HCr. Okay, you can see the shift's about 1.0 ppm, and your data sheet tells you that's an HCr shift. And that just tells us that there's another carbon next door. Not an exciting one like a carbonyl or a benzene ring, but just some kind of bog standard carbon next door. So we can do that and say, right, we think we've got that in our structure. Again, just from looking at this peak. But the thing that really makes the key to now connecting to the rest of the structure is the splitting. So don't ignore the splittings, because they're actually usually the most informative thing that you've got to work with. So here it's split into 3, it's a triplet. And what does that mean? Well, remember your n+1 rule. If it's split into 3, it means that there are 2 hydrogens on a next door carbon. Okay, the splitting number is one more than the number of hydrogens on adjacent carbons. So we can write down, okay, that must be CH2 to have caused that splitting. So we can say, right, we've got CH3, CH2 just by looking at this peak. So again, we'll write down, that's important, you document your thinking, because an examiner needs to see that you worked this out, that you didn't just kind of guess things. So you can say this is a triplet, and that means that there are 2 hydrogens on adjacent carbons. Okay, so we've got CH2 here, and we know, remember, that carbon has 4 bonds. So if you've only got CH2 there, there must be a bond to something else. Sorry. As are what we've learned so far. So we've now done everything we can about this peak. So let's just say, right, we've dealt with that one so that we don't get confused and come back and think we've still got that peak to worry about. So we'll cross that peak off, say, right, we've dealt with that one. And on our growing structure, we'll say, right, these 3 give you the peak at 1.0 ppm. Okay, so that comes from that set of 3 hydrogens. So what do we do next? Well, what we do next is say, well, we've deduced there must be a CH2 there, because that splitting into a triplet means there must be a CH2 next door. But those CH2 hydrogens must also themselves appear in the spectrum. There must be a peak corresponding to those CH2s. So how do we find which one it is? Well, what we look at, first of all, is the peak areas, because it must have a peak area of 2. So it can't be this one, because that has an area of 1. So we know it's not that one. And similarly, it can't be this one, because although that has the right area, it doesn't have the right splitting. Okay, this is only split into a doublet, and that means that there's only 1 hydrogen on an adjacent carbon, and you can see that's not the case here. This CH2 has got 3 hydrogens on adjacent carbons. So we can rule out this peak as well, because it's got the wrong splitting. This one, however, has got the right splitting. Okay, split into 4, that means there are 3 hydrogens on an adjacent carbon, and you can see that fits with the structure, because if this peak is the peak at 2.6 ppm, it's split by these 3, so it should be split into 4, and indeed it is. So we found that CH2 peak. Okay, so let's document that one next. Okay, so we have got this CH2 comes from the peak at 2.6 ppm. We say about it, well, we can say that it has an area of 2, because it's due to 2 carbons. We can say that it's a quartet or quadruplet, because there are 3 hydrogens on an adjacent carbon, which is consistent with the structure we've drawn down. So quadruplet means that there are 3 hydrogens on an adjacent carbon. We haven't thought about yet is, what about its chemical shift? So always think about all of those things: area, chemical shift, splitting. You've got to think about all of them for each peak. And the chemical shift is going to be really important, because we know that there's got to be something here, right? We know that there's got to be something on the end of that structure there attached to the CH2, and the chemical shift is going to give us a clue about what that is. So the chemical shift here is between 2 to 3 ppm, and if you look at that on your datasheet, it tells you that that could mean it's next to, for example, a benzene ring or a nitrogen, but you haven't got either of those in the structure, so the only thing that can be is next to a carbonyl group. So we actually know that we now have this structure, and again each carbon must have 4 bonds, so we know again there's a bond to something else sticking out on the other side of that carbon. So that's really big leap forward, because we've now got a substantial chunk of structure from looking at these 2 peaks. Make sure we finish documenting it. So we say that this has an HCCO shift because it's in that 2 to 3 ppm region. Okay, so we've learned all of that from this peak. So now we cross it off and say, right, don't look at that peak anymore. The remaining hydrogens in the structure must just come from these other 2 peaks at around 4 and around 9 and a bit ppm. So what do we do now? Well, we have got 2 more peaks to interpret. We've got a bunch more carbons and hydrogens and things to interpret, but we can't directly work out what's on the other side of this carbonyl group because we've got no hydrogens on there, so we've got no information directly about what's next. So we're going to just leave that bit of structure where it is for the moment and then join it on to another bit of structure that we're going to deduce by looking at these remaining peaks. Okay, so we just keep that documented, ready to build into a bigger structure in a minute, but now we're going to start looking at these 2 peaks. Now at this point you've got 2 split peaks, and you know that split peaks arise when you have hydrogens on adjacent carbons. So when you think about it, it's kind of obvious that these 2 peaks must come from sets of CHs that are next door to each other. So we know we're going to have a structure that has 2 carbons like this, just from the fact that you've got the 2 split peaks like that. So again, let's just pick one of them and start with that. So let's look at this one. Okay, so 9.5 ppm, very characteristic chemical shift. You look at that and you think, okay, that is an aldehyde hydrogen. Okay, so 9 to 10 ppm is where you get aldehydes. So let's document what we know about this. It has an area of 1 because there's just 1 hydrogen, and it has this HCO shift, 9 to 10 ppm. Make sure that you're very clear about the difference between HCCO, which we had here between 2 to 3 ppm, and HCO. So HCCO means you have hydrogen, let's just pointer here, you have hydrogen bonded to a carbon, and then that carbon is bonded to another carbon, and then that one has the oxygen attached. So it's HCCO. When you have a peak between 9 and 10, that's different, because that means you have this H bonded to a carbon, and then the oxygen is directly bonded to that same carbon. So you have that in your structure. So HCO. And that's what the chemical shift of that tells us. So that's a huge advance because we now know this compound has an aldehyde group in it. So again, you think, what have I not done? I've not thought about the splitting. So the splitting is a triplet, and that means that you have 2 hydrogens on the next carbon. So let's write that down. Triplet means 2 hydrogens on an adjacent carbon. So we can say, okay, we've got to have that. Because this peak can only be a triplet if you have a CH2 there. So we can, just from looking at that peak at 9.6 ppm, we can deduce that we've got this element of structure present. And just like we did with this first chunk of structure here, we can say, right, if this CH2 must exist, it must also appear in the spectrum somewhere. So there must be a peak corresponding to those 2 hydrogens. And obviously we've only got 1 peak left because we've dealt with that one now. So it's got to be the peak at 4 ppm. So just make sure that we haven't gone wrong somewhere and make sure everything fits. But that must be the peak due to this CH2. So we can say, right, this hydrogen gives rise to our peak at 9.6 ppm. These ones should give rise to our peak at 4, but before we write that down, we're going to check it fits. So this one has an area of 2. Due to 2 hydrogens. So that fits. Okay, fits the area of 2. It's a doublet. And so it should be, because the next door carbon, this one, has just 1 hydrogen on board. So n plus 1 is equal to 2. So it's a doublet due to 1 hydrogen on an adjacent carbon. But what about its chemical shift? Because what we now need to do is to say, well, how does this bit of structure connect up to that one? And the chemical shift of that's going to be very useful for doing that. If we tried to just join these 2 bits of structure together directly, you could see there would be 2 problems. The first would be that it wouldn't fit the molecular formula, because although we've then accounted for all of the carbons and all of the hydrogens, we haven't got all of those oxygens accounted for. So we've got a missing oxygen, but also the chemical shift of this around 4 ppm isn't consistent with just being next to carbonyl groups, because it's next to a carbonyl on that side, but it's also would be next to a carbonyl here, and that wouldn't account for a shift of 4 ppm. If you look at your data sheet, it tells you that you get that kind of shift when you've got something like an oxygen or a halogen attached. We haven't got any halogens, so there must be an oxygen attached. So we can deduce this. We can deduce this from the chemical shift. There must be an oxygen attached, and remember, oxygens form 2 bonds, so there will then be a link there. Okay, so that's really important because it accounts for the final oxygen in the structure, and it's going to then make it possible to just join these 2 fragments together. So we can say that we have a chemical shift is HCCO. Sorry, HCO rather. We have an HCO shift, which is 3 to 4.3 ppm. Okay, and that told us that we had this bit of structure. So we've now documented all of the evidence, and we've got these 2 fragments. So this final piece was the peak at 4.0 ppm. So we now have 2 fragments. when you add up all of the atoms, they account for the whole of your molecular formula. We've got a bond with something on the end of it here. We've got a bond with something at the end of it here. So all we have to do now to get the final structure is join them together. There it is, your final answer. And you can see it fits all of the facts. All of the hydrogens are accounted for in terms of where they appear in the spectrum. They fit the shifts, they fit the peak areas, and they fit the splittings, and you have to check that everything fits. The thing with this is that if you ignore one of those parameters, you can get something that looks like it fits, but it really doesn't. And so it's important to sort of double check you've got everything there. And of course, you've got to check it fits the molecular formula. And you've got to check that it fits the other spectroscopic data. So in our case, yes, it does have the carbonyl groups that accounted for that infrared band. So there you have your answer. To make sure you get full marks in a question like that in an A-level exam, the important thing is that obviously you get the structure right, but also that you document all that evidence, that you basically make sure you've explained all the splittings, all the shifts, and all the peak areas.